let's go have a look at this study. Now, in this study, there's only a few things that I really want to bring up. So there's a kind of a somewhat more prevailing argument for AI proponents that if you use small language models, so as opposed to large language models, then you're going to be able to reduce the size of the model and its power consumption that you need. And I've started to look into the kind of the viability of using small language models, and they're also called like narrow AIs, to see whether that's true. Here's one of the first studies that I thought of bringing up. So what they did is they took small language models and they benchmarked them. And here's the sad part. They took 0.4B to 10B parameter models. We'll get into what the sizes mean. We'll just cover this kind of briefly and go over it. Essentially, compact small language models achieve competitive results while maintaining a balance between performance and efficiency, making them viable for deployment in resource-constrained environments. Okay, so far so good. However, achieving further improvements in accuracy requires switching to larger models. In other words, as part of this study, they hit an upper limit of these small language models. Anything beyond that would require you to have to step up to the large language models, thereby negating any possible benefits that you would get out of running a small language model, including power consumption. These models generally outperform their smaller counterparts, no duh, but they require much more computational power. We observed that for 10% performance improvements, okay, right here, models can require nearly a 4-time increase in VRAM consumption. The disparity between power consumption and performance gains when you have to go from small language models to large language models becomes wide, highlighting a trade-off between effectiveness and scalability. Besides, the multilingual performance analysis reveals that small language models tend to perform better in languages such as Python, Java, and PHP, while exhibiting relatively weaker performance in Go, C++, and Ruby. However, these differences are not significant. In other words, the language doesn't really make much difference. You're going to get basically the same performance output from your small language model as you are from the big language model. And when it comes to the 0.4B and 10B, those are parameters. Those are in terms of billions. So we're just going to go down here, and I just want you guys to have a look at two things. One is the kind of hardware that's required to even run these small language models that they ran for this study. You need a 20-core CPU, 32 gigs of RAM, and an NVIDIA L4, which has 24 gigs of RAM in it. The second piece of hardware was a 10-core CPU with 26 gigs of RAM, and an RTX 3090 with 24 gigs of RAM in it. That's to run the small language model. For what? Basically the same performance that you're going to get at the bottom level of the large language models. Well, that doesn't really say much about the small language models, does it? It's not a very, let's say, appealing argument. And just to go down a little bit over here, you can see that the parameter sizes, they kind of have a bunch of them all laid out here. This is essentially an indication of how smart the model is supposed to be. The idea being that the more parameters you have inside the model, the smarter this thing's going to be. So a small language model like one at the top here, Polycoder 0.4 billion parameters, would be kind of like the least smartest. That's the intent here. And some of the big language, the large language models have like, now they have like 100 billion, 200 billion. So these small guys, just in terms of parameter size, obviously they can't really compete at the same level, right? So I thought this was a good start into exactly how these small language models operate, and they don't really operate that well.